We're going to talk about optimization now, and it's similar to related rates, but I want to differentiate the two. And when we read the question, I'm going to talk about how you know whether it's optimization or related rates. And just like related rates, I'm going to go through one step at a time for each particular video so that you can get a good grasp on how to solve an optimization problem. So here's our question for example 1. A manufacturer wants to design an open box with a square base. So notice it's an open box, that's important. They want to use 108 square feet of cardboard. So this figure right here is surface area, okay? Now the box itself has volume once you use that square footage to make the box. What dimensions will produce a box of maximum volume? And I can tell you right now that key word here is maximum, okay? When you read words like greatest or least amount or cheapest or most expensive or smallest, um, any kind of superlative or in this case maximum or minimum, okay? Maximum means the greatest. That's an optimization problem, okay? So when you read those superlatives, you'll know it's an optimization problem. Related rates has to do with the speed or the velocity or the rate in which something is changing, whereas optimization has to do with greatest or least or a superlative. So as we read through these examples, that's how you know it's optimization. Just like step 1 with related rates, we're going to draw a labeled picture. Now, I drew a box that they're going to make with this cardboard. You know, you might be thinking, well, what does that cardboard look like? It doesn't really matter, but chances are it's probably just a sheet of cardboard. It might look like this. It's 108 square feet. So basically, you're going to take that and you're going to make a box out of it. How big is 108 square feet? I don't know. It might be the size of, say, a kitchen or something. A bedroom that's 10 by 10 would be 100 square feet. So anyways, that's how big that cardboard is. You want to mold it into a box. Now, my picture, I was clear about the fact that the top of the box is open. So I will not be using cardboard here. This way you can reach down into the box or whatever you want to do. All I know is I'm using 108 square feet to make the box, and I know that the base is a square, so when I draw my picture, I'm going to label the base X and X for the side links. The height, I do not know yet either, right? There's a lot of different ways to draw the box, okay? There's a lot of different possibilities to make a box out of this. And so this might not be a perfect picture, but it just kind of generally represents the boxes I could make. And notice I notated here that I used 100 square feet to make the box. So your box might look different. It might be taller and skinnier. It might be lower to the ground and shorter. We want to figure out the box, though, that produces maximum volume using the least this amount of cardboard. So that's it for step 1 of example 1, drawing a labeled picture. Equally as important as when you're doing, say, related rates for step 1. Okay, let's read example 2 together. It says the sum of the perimeters of an equilateral triangle in a square is 10 inches. Find the dimensions of the shapes that produce a minimum total area. So again, how do you know this is optimization? You will see this superlative minimum or least amount of total area, and you know it involves optimization. You know, optimization, the word optimization means the best case scenario. And in the real world, many times people are actually, that is their job description. That's what they do. They work in optimization to save companies money. So spend the least amount of money to produce this object or whatever, produce this product. So again, let's read this question. Find the dimensions of the shape that produce a minimum total area. Well, let's read the question one more time. The sum of the perimeters of equilateral triangle in a square is 10 inches. So let's just, for step 1, let's just go ahead and draw our equilateral triangle. We know then that All three sides must be x because it's equilateral. And that's pretty much it for now. You can draw this dotted line for the height if you want. And then for the square, well, all the sides are equal, but it might not be the same side lengths as the equilateral, so we're going to call the side lengths y. Now, that's all we really have to go by right now as far as, a picture is concerned. Now, I guess you could say, okay, well, if you add up these two perimeters, not the area, but the perimeters, you get 10 inches. So basically, if you took these three sides and these four sides and add them up, 7 total sides, you get 10 inches. And again, the question is asking, find the dimensions of the shape to produce a minimum total area. So we'll get to more into answering the question as we move forward. But for right now, this is a good illustration. It gives you an idea of what you're dealing with. Let's move on to example 3 and looking at drawing a picture for it. Okay, here's example 3. And this one is more involved. It's more challenging. And so this one might take us a little bit longer. All right, all units in a 30-unit apartment building are rented out when the monthly rent is set at $1,000 a month. So basically, so somebody owns an apartment building and they charge $1,000 a month to live there. This problem is telling us that all 30 units are filled up whenever that happens. So you might think, well, great, just keep it that way and you'll always have tenants in your apartment. You'll be making $30,000 a month on rent. But let's keep reading the question. A survey reveals that one unit becomes vacant with each $40 increase in rent. So what that means is, let's say we started charging $1,040. One unit would become vacant, so now there would be 29 people. You would lose somebody. You would lose a tenant. Now, if you increase another $40, so 1,080, you would now have 28 people. You'd lose somebody else. They don't want to stay there if the rent keeps going up. People are going to leave. They don't want to pay so much. Suppose that each occupied unit costs $120 a month in maintenance fees. Now, I really like this problem. It was written really well by someone, and it's just very, very practical. Okay, because if you've ever rented an apartment or a building to somebody, it costs money to keep it up. So suppose each occupied unit costs $120 in maintenance fees, fixing water heaters, whatever, fixing maybe electrical problems. What rent maximizes monthly profit for the owner of the apartment building? So here's the thing, they might not be making the most amount of money by filling the apartment up. Maybe they should increase the rent some so that they don't have to pay so much in maintenance fees when the unit's full. For example, if everyone's inside the apartment building and you have 30 full units, you are going to be spending $3,600 a month in maintenance fees. So maybe you don't want as many, so maybe you should increase it some. So here's my picture. It's pretty much just an apartment building that has 30 units in it. There's really not much more, we can draw here. We might put like a money sign in one of these units because the cost of rent's going to change depending on whether you charge 1,000 or 1,040 or you keep bumping the rent up. But that's it for step 1. For example 3, we're just drawing a picture of the apartment building to try to get a feel for what we're trying to solve for, which again, we want to charge the rent that maximizes profit for this apartment building owner. So that's it for step 1. We're only going to do 3 lessons for now, 3 examples rather. Next up, we will look at step 2, which is the determining the constraint equation.